Hi. Today we'll look at the PAT paper from 2008 going to question 23. Okay, so question 23. We're told this problem will consider the possibility of storing electrical energy in capacitors made of two small parallel plates, each of area capital A, separated by a thickness small d of a dielectric with electrical permittivity P. So the capacitor will store a charge Q equals CV, where the capacitance is given by C equals P capital A over D, and V is the voltage across the capacitor. And we're told, given that the work done in charge on the capacitor is W equals Q squared over 2C, show this equation here, W equals PAV squared over 2D. Okay, so let's do that. So we know we've been given that W is equal to Q squared over 2C. And what we notice that there's no Q's in here, so let's eliminate Q. We know Q is CV, so let's plug that in. So we get CV all squared, replacing the Q with CV, that's equal to 2 over 2C. Well, that's C squared over 2C, so that's C squared V squared over 2C, which is simply C V squared over 2. Okay, that's looking all right, but we don't have a C in here. But we have an equation for C up here. We know C is PA over D, so let's replace that in. Well, that's equal to PA V squared over 2D, which we know is the required answer. Okay, so the next part of the question says that this work done is equal to the energy stored in the capacitor. So in practice, a capacitor is limited by something called a breakdown voltage of its dielectric, which is proportional to the thickness. And we're given that this breakdown voltage, Vmax, is equal to B, some constant, times D, the thickness. And we're asked to determine how the maximum energy stored in the capacitor depends on the mass of the dielectric M and its density, capital D. So essentially, we're asked to find how our equation W equals W equals PA V squared over 2D, so that's the energy stored. We're asked to find how the maximum energy stored, so the maximum value of this, depends on the mass, little m, of the dielectric and its density, capital D. Okay, well, what is the maximum? Well, Emax, the maximum energy stored, will correspond to a maximum value of the voltage, V. So that will be PA V max squared over 2D. We're told Vmax is BD, so that's PA B squared D squared over 2D, so that's B squared D over 2. Okay, well, what do we know about the product of A, its area, and D, its length? Well, area times length gives you a volume. So that gives us the volume of the dielectric. So P volume of the dielectric, B squared over 2. And well, we know volume is mass per unit density. We've been given here density as capital D. So subbing that into here, we get that's equal to P times the volume is M over D times B squared over 2, which tells us that the Emax is equal to PM B squared over 2D. Okay, now for the last part of the question. Well, here we're told for a dielectric with P equals 2 times 10 to the minus 11 F m to the minus 1, B equals 2 times 10 to the 7 V m to the minus 1, and D equals 1,000 kilograms per meters cubed. Calculate the maximum energy that can be stored in a capacitor with a mass of 1 kilogram. Okay, well, we know Emax is equal to MP B squared over 2D. And we have all these values. So plugging that in, we get it equal to the mass 1 times P, 2 times 10 to the minus 11, times B squared, 2 times 10 to the 7 squared, over 2D, 2 times 10 to the 3. Okay, well, 2's cancel, so that's 1 times 10 to the minus 11 minus 3, so that's minus 14, times 2 squared is 4 times 10 to the 14, and that comes out as exactly 4 joules. And then for the last part of the question, we're asked, comment on the practicality of using a capacitor of this type to smooth the output from a 1 kilowatt domestic wind turbine in a gusty area. Well, 1 kilowatt is equal to 1,000 joules per second. And this tells us clearly that 4 joules is too small a capacity to have any useful effect. So it wouldn't be of any use. And that's the answer to the question.